So first of all, I would like to thank the organizers for the invitation. It's a great pleasure to be here. And what's going on? It's took too much. Too long. Yeah. Okay. So yes, I will speak today about urban air mobility. This is a field in which I've been working in the last few years. And this is like I will speak about a few works in collaboration with Rémi Delmas, Youssef Hamadi, who were at the Uber Research Center in Paris on Uber Elevate. Mercedes Pellegrin was a postdoc in my group, and she's now at FICO. And Tom Portolo was also a postdoc in my team, and is now at the University of Artois. So the talk, so the outline of the talk today is this one. So I will start by introducing urban air mobility and what I mean with this. And then I will speak about how mathematical optimization can contribute in urban air mobility and guarantee safety in particular. I will focus on this aspect. And then I will go through a more formal definition of the problem. And I will focus on the most important, so most interesting for me part of the modeling of the problem, that is the safety constraints and how we decided to model them. And then I will show you some computational experience, and if I have time, I will speak about some ongoing work. So feel free to stop me anytime for questions if something is not clear. So what is urban air mobility? So you might, I guess that all of us know that in widespread cities, we have a problem of ground traffic, congestion in particular. So there have been several approaches to try to tackle it. And in particular, urban air mobility is thinking about using the third dimension, so the sky, in order to decongest a little bit of the traffic. So this, of course, it's already present in some cities. For example, in São Paulo, there are people who are using helicopters to move around. But the difference with this is that it will be kind of like a air traffic, like air taxi that will be available in general, and we want it to be sustainable actually. So the idea is that there will be well, in cities. So here I put New York, Paris. So like these are the cities in which the discussion for proposing this service is more advanced, let's say. So they're still really working, and they're doing some tests on flights since at least one year in Paris and New York. And I know that I look it up about India, and actually apparently there are discussions in India as well to propose this service, but they are less advanced than in other cities. So what is the idea? So, and what is this vehicle here? So it looks like an helicopter, but it's not an helicopter. It's called the eVTOLs, which stands from Electric Vertical Takeoff and Landing Vehicle. And actually it takes off and land vertically as an helicopter. So the advantage is that it doesn't need a lot of space to take off and land as opposite with respect to aircraft. It's completely electric. And on the cruise phase, it's pretty efficient. So they can, like propellers actually move, or there are propellers that are made for the takeoff and land, and some others that are for cruising. And so this is, the idea is to integrate this service in the, like a public transportation offer as an alternative to taxi. At the beginning, it will be, well, like a few of them, and maybe expensive, but on the long run, there will be like a shared taxis, etc. So it will be like the cost will be sustainable, not very far from a taxi, let's say. So that is the idea. However, the point is that we have to integrate it in the system, and there are several questions that are still open. First of all, infrastructure. So how to make infrastructure available. So you can use heliports, but we will need to install new ones. So we will call them vertiports. And also, as they are electric, they have to be connected to the grid, they have to be provided electricity, etc. And but the focus of today's talk is safety. So we need to guarantee that we propose a schedule of these vehicles so that they do not crash, of course. And so actually optimization tools can be used to help this traffic control. So I don't know if you see, but it doesn't matter because I will explain. So there are mainly three phases in the air traffic controller controlling. This is valid also for civil aviation, actually. So there is the green part is the so-called strategic phase in which the planning and scheduling of the flights is done in advance. Then there is the second part that is in yellow here. So it's after departure time. Is the tactical deconfliction, which so where we suppose that some disruption might happen, and then we need to re-optimize in order to make the schedule that became infeasible feasible. And then there is the red part that is detect and avoid, where like the pilot decides. So it's we're really about to crash, and then they need to decide what to do. So we do not. We need to try to fix the situation before we arrive at the red part, but and here in the red part, mathematical optimization cannot do anything anymore. So we will focus on the first two parts. In particular, I will actually start with the tactical deconfliction. So, but we have a paper on a conference paper on this part, and this is the ongoing work. And this other paper is more on the re-optimization part, the tactical deconfliction. I will start with this because actually we use this problem as a sub-problem of this one. And the idea for the strategic deconfliction will be to have a robust solution, which is robust to the disruption that we will see here. Okay, so far so good? Yeah. Okay, so now mathematical optimization. So let's start with some formula. So I will just start with what we ideally would like to have, which is guaranteeing safety that is given by these constraints. So now I explain it. We have capital A is the set of aircraft. So for each pair of aircraft, and for each instant in the time horizon, capital T, we would like the position, so xi of t is the position in the sky of aircraft I at time t. And we would like that the distance basically between I and j is at least capital D, that is our safety distance. So unfortunately, this constraint has several aspects that are but that makes it complicated. First of all, this is usually a Euclidean distance, so it's a nonlinear, no convex constraint. And second of all, here t is really it's not cannot be sampled and discretized. We need really to consider every instant in order to guarantee safety. So you see that here that we have a non-convex constraint, which actually infinite amount of them. So we don't want in the re-optimization phase to have a problem so difficult to solve. So we will see how we will specialize and simplify this constraint in the urban air mobility situation.
Infinite amount of them, because what is it?
T. Yeah. And unfortunately, if you discretize, you don't know how you can discretize it, because there might be that between two samples there is an infeasibility, right? Okay, so what is the idea? So the idea here, I have the flight 1, in red, and I have a flight 2 in blue. So at time 0, they are in this position. They need to take off. And their trajectory is fixed, is this and this. So if they take off at the same time, and they have the same speed, they will find themselves in the same position at time 5, and of course there will be a crash. So we want to avoid this. So what could be a potential solution? A potential solution can be that we ask F2 to leave at 0, but to F1 to wait. And so that when F2 is here, F1 can go here safely. And then F1 will just arrive a little bit later to the destination. Okay? Clear? Yeah, okay.
Sorry,
yeah.
What about vertical separation?
Oh, vertical separation, so that is a good point. Actually, vertical separation is, so even in classic air traffic management, you consider only the flights that are flying at the same altitude. So you can consider a 2D problem, and you consider that they are flying at the same altitude. So, and you do not want them to change altitude on the flight, on the cruise. Yeah.
But shouldn't the signing of altitudes be done at the same time?
Say again?
Shouldn't you be choosing the altitude and the departing time simultaneously?
That can be done in instances. So, like basically, well, maybe I will use this. So basically, the decision on the altitude is, and it's made at the takeoff. So takeoff, it's the only place in which you change altitude. And so in our modeling, we can deal with it by splitting the different corridors and assigning it to a different path, the different aircraft. Does it answer to it? Yeah. So the point is that actually there will be, so this is how it will work in the US. So there will be a corridor, so some given altitudes that are devoted to this service. And they define some kind of roads in the sky, so virtual roads in the sky, and the vehicles cannot really get out of it. So they cannot change like altitude in the cruise phase, and they just have to follow the road, and that's it. So that is how it's organized. And so basically, for each of the road, there is a direction, and they have to keep it. They cannot overtake each other. So it's it's very regulated, very regulated. And so the idea is that we want to decide. I mean, like actually, our only decision is really the scheduling. I don't know why it's. The scheduling of the flights, because they cannot change path online, basically. And so these corridors will be connecting vertiports, and they are 3D, and we have the most complicated parts in which we have to guarantee safety is where actually the corridors cross in the junction, the nodes that I call junction. So in practice, the solution that we would like to obtain is a kind of schedule. So here I represented as a graph the two trajectories that we had before for the flight 1 and 2. So X1, 2, 3, 4, 5 are the nodes. We have a node for each of the vertiports, and also a node for the junctions, of course. And so what the safe scheduling for F2 was like we leave from X1 at 0, then we arrive at X3 at 5, and we arrive at X4 at 10. And X2 is, we leave F1, sorry, we leave X2 at 5, we arrive at X3 at 10, and we arrive at X4 at 15. And so finally, what happens is that our constraints that will allow safety is that we need F1 to arrive at this point, which is the common point, after the time in which F2 is arrived at this point, plus a kind of safety time that I will define more formally later. Okay, is the problem clear? Okay. And then at this point, we'll go to the more formal definition of the problem. So what we did was to define a graph, and we have like a set of nodes and a set of arcs which are oriented. Set of nodes are divided into mainly 3 colors. So we have the inner junctions that are in green, and then the red points are the vertiports. We split the vertiports in two, so the takeoff and the landing part. So actually, we have here this vertiport that is unique. So we separate the two parts, and we have the takeoff can only go in this direction, and the landing, so they come from the corridor and they land here in the blue. Takeoff in the red, landing in the blue. And so this is input data. And you can see that if you need more corridors and more altitudes, you can split the graph and have in parallel some corridor that goes from here to here, for example. Okay, now, so the other data that we have is for each of the flights, we have the path that it has to follow. So you can see here, for example, so it will always start in a red. It can pass through, typically will pass through several greens, and then it will arrive in the blue. So this is a feasible path from a flight that has to go from here to here. So, and the path is expressed as just a sequence of nodes. That's it. And then for, of course, the two consecutive nodes have to have an arc that links them. Otherwise, it's not a feasible path. And then the other thing that we have as an input is the nominal, what I would call nominal scheduling, which is the scheduling that we decided the day before, which is represented by T hat. So for each of the, so we have an element for each of the flights, I, and each of the nodes, M. So this is the time at which flights I has to pass through like node XM. Okay, so this is all, everything is input. And then indirectly, we have the speed at which Fi traverses XM, because we assume that along an arc, the speed is constant. And so we having the T here and the T here will allow us to compute the speed as well along each of the arcs. Okay, now I was saying that we will start focusing on the tactical phase, but potentially we can reuse the same model in the strategic phase. How would you do? So we will just have as an input the ideal schedule, which is the path is just the shortest path between origin and destination, and the schedule is the desired departure time. And then the arrival time is the one given by the average speed. So this can be an initial path, like an initial ideal schedule that we need to fix. However, we will focus on what I was saying, the tactical phase, in which we have a nominal planning, which is not feasible anymore because of some disruption. And we decided consider three types of disruptions. One is just a delay. The second one is we need to accommodate a new flight that wasn't planned. So suppose that we have, I don't know, hospital that has to transport some patient, etc., or a police or whatever priority flight we have to accommodate. So we try to give priority to this flight and adapt the schedule to this priority. And then third is unexpected traffic, which can be an intruder that wants to make some problem in the sky. So the first one can be kind of predicted. So and the other two are less unpredictable, more unpredictable scenarios. And the third one is even more complicated because in the second case, for the priority flights, it's a collaborative situation. In the third one, no. Okay, so let's speak about the mathematical optimization formulation. So as I said, degrees of freedom are, we can let the flight wait for the departure, so change the departure time. And we can also, at each of the junction, decide to change the speed. So we can change the schedule all along the path of each of the flights. We cannot change the path for the moment. And then, so this is and the output is the new schedule, which is feasible with respect to the disruption that we had. Yes?
So this means that the disruption can be before the takeoff, also or during.
Yes. So there will be some flights that are already flying while the disruption is coming, and some flights are not flying. So, of course, this that's a good point. So the departure reschedule is just for the flights that didn't start yet. So actually, we for the computational results, we consider some batches of flights. So some of them has to start now, some of them in 5 minutes, etc. So based on when they are supposed to leave, we can or not reschedule based on the disruption. Yeah.
Just going back to the vertical separation question. So
Yeah.
If the corridors are east-west and north-south, like in the picture.
Yeah.
So is there a constraint to design the north-south?
It's hidden here because actually here, sorry, I will go here. Actually here we have two nodes that are one over the other, and there is a hidden arc that is the vertical direction. So we have here in the same node the vertiport and the vertiport junction. So we will have an arc that goes from here to here, which leads us to the altitude.
Okay, but one can design this north-south corridor at a higher altitude and east-west.
Yeah, so let's say that the position is not meaningful with respect to the real position of the waypoints. So this is just a graph representation. So you can have here in parallel something else that goes here, which is at a different altitude. So these points here are not really like representing their position in the sky. Let's say it's just a graph representation of our corridors. Other questions? Yes. Sorry.
Can they
Wait.
And the weight cover.
No. We cannot wait in the air. No. So that's also a good question. Actually, we have a nominal speed, and we can change it only of more like a plus or minus 5%. So it's a very like controlled modification. And the reason is because we want the passengers to feel safe and not to feel the changes. And this is also happening in the classic aviation. So like in the re-optimization that I'm doing, it's like between 5 and 10%. We will see how it changes in the computational results. And then there is the red phase in which whatever is allowed. So you can speed, you can change route, etc., just to avoid the crash. But that is really the last minute recourse, and the pilot is responsible for that. So these are very, very tiny modification to the schedule, but we will see that typically that they help recovering a feasible solution in at least in the first two scenarios. Other questions? Okay. Yes. So yes, just one thing that I kind of somehow sometimes I will hide it is that actually the planning is not really 1 second, like one precise instant. The planning is more some time intervals that are safe because of some safety reason, of course. So it means that actually F2 knows that they can live between the time instant 0 and 1 from here, and the F1 from between 5 and 6. And then 5 and 6 will be the instant, so the time interval in which F2 has to go in the junction, and it will arrive between 10 and 1. And then F1 will arrive at between 10 and 11 here, and finally here. Yes?
Are you considering the node capacity?
Node capacity?
Yeah. Are you considering exactly one vehicle can be added to the node?
Yeah, just one. Yeah, in the junctions, just one. Yeah, one at a time. Then, of course, in the vertiports, there can be several paths, etc., to manage the operational parts, but we will just hide it in this model. But yeah, we suppose that for each capacity, we have just one corridor. And so if you have several corridors, one after the other, we will have separate corridors that have capacity 1. Okay. So actually, our decision variables are for each flight and each node in the path. Along the path of that flight, we will have the scheduled times, which is represented by T earliest or early passing time and T latest. So these are the two the intervals. And so we know that the schedule is safe if we respect this interval. Okay, and then we have other auxiliary and dependent variables, which I will just not detail for the moment. I will speak briefly later about them. So, okay, so let's look at the objective function. Objective function is minimization of this quantity, which is for each of the flights and each of the nodes along the path. We want to stay, to have the new schedule to be as close as possible to the nominal one. So we want to T early, so we can have a T early minus T hat early, which is the input, the nominal schedule. So we check the difference and we actually have our measure. Plus, we have some part here that is only specific for the second scenario, which we have the priority flight. We want to prioritize the departure at the desired time of the priority flights. So we will have a big M that says that we want as much as possible to respect the desired departing time of the priority flight. And then if we can accommodate this, we will optimize the rest of the schedule. But this allows us also to delay the departure in case there is no feasible solution for T year equals to the desired departure date. Okay, so let's now focus on the safety constraint that I showed you before that is very ugly and complicated. And let us just consider that we want to solve this problem in a few minutes, not more, because it's an operational problem and we have to react very, very fast. Okay, so actually we do not have among our variables the position of the flight, but we have actually indirectly their position because of the schedule. So actually we can write the separation constraint as this. So we have that the time at which flight I passed through node M minus the time at which flight J passed through the node M has to be greater or equal than safety time. And we will compute this based on the safety distance. And in particular, we will consider two families of conflict, the trailing and the intersection. Trailing is easy because it's the situation in which both flight takes the same arc. In this situation here, so suppose that, overtaking is forbidden, so whoever enters first the arc will exit the arc first. And we said that as an hypothesis, we say that along the arc, the flight has a constant speed. And so it's sufficient to consider the beginning and the end of the arc to impose the safety condition. So at least we have a limited number of constraints. How do we write them? So for the initial node, we have this formula here. So we have that actually this part here is representing the distance that flight high I, which is supposedly for the moment entering first the arc, can fly before J enters the arc. So this is let's say, when we want that the flight I, so the first flight, will be at least at a distance d from the initial node when j arrives at the initial node, okay? So you see here that again we have a product of variables because v is a variable and t are variables. So actually we simplify this by making it a little bit more conservative, and we just considered the lower bound on the speed. And so now we have a linear constraint on the times, and on the right hand side we just have some data, okay? So there are just two of them instead of an infinity of them, and they are simpler because they are linear now. Then we have a similar situation at the end of the arc, because we have that the left-hand side represents the distance that the flight j that is coming later should fly before coming at xm when I is at xm. So actually when I is here, we want the distance, so the flight to be at least here. And so similarly, we simplify the constraint and consider the lower bound. So we have a more conservative constraint, but like we want to guarantee safety. So it's simpler to solve and also more safe, let's say, if we can say. And so we will use this. Is the trailing conflict clear?
So the velocity is constant.
In this case, I just use the lower bound. So this is why. So basically, I could have be less conservative if I use the real speed, but it will give us a nonlinear constraint, which we know. I mean, we do not expect to solve this nonlinear problem in a few minutes. Let's say. So this is why I say it's more conservative, because I use the lower bound on the speed in order to impose the safety constraint, while I could have just needed the speed itself. Okay, then there are three other kind of conflicts. The conflicts in which the flights are not using the same arc, but they are converging to same node. And then the case in which one flight is leaving the node and the other is entering the node. And vice versa, I have the case in which two flights are diverging from the same node. I have to take care of this as well. Yes? With this one? So, like, it depends on what you mean waiting. So, waiting is like like decreasing the speed up to 5% is possible. Yeah. So I will show you that we have unfortunately, some infeasibility. So there are some cases in which there is no feasible solution for the problem, even if we allow a larger increase, like decrease or increase of the speed. So yeah. But I mean, I will say that here as well, it's important to prove fast that the solution, there is no solution for this, and to make other actions, let's say. Okay. Then so let's consider just the first one for explaining what we did. Again, we were over conservative in our constraint that we imposed to guarantee safety here. And the reason is because we wanted to have a simple constraints. So the idea is that, so suppose again that Fi has to go to xm before xj. So this is the trajectory of Fi, and this is the trajectory of Fj. So when we want to identify the position in which the flight start going in a dangerous situation, which is actually this point. Why? Because actually this radius is of size d, which is the safety distance. So when we start touching the trajectory of the other flights, we start to be in the situation in which we need to impose some constraint to make it safe. So what we are going to say actually is that flight J is allowed to be here when flight I is already here, not before. So we can write it well, this is just to say, well, we have a similar situation in the other three, but like just to explicit the constraint. So TIM, so the time at which I is here, has to be less or equal than the time at which J is in this position here. And we can write it similarly to the previous constraint. We just need an extra coefficient to take into account of the angle between the two arcs, and that's it. And similarly to the others. So everything is linear. And now, so let's go to the, so further modeling details. So up to now, I suppose that we have an order in which the flight has to pass, but actually we won't allow also to exchange. And so we will actually have these junctions saying either the I pass before, and then we need to before J, and then we need to impose these constraints, or J passes before, and so we need to impose this constraint. So now I think you're convinced that it's a mixed integer linear problem. And yeah, the bound speed, I already spoke about this, and then we have some technical constraints about climbing arcs that I was mentioning before, etc. But they are, I mean, let's say more classic constraint that can be easily written as a linear, so I will not detail them. I have the full model if you want, but it's a very like long, etc. So less interesting. So I will have just a look at the time. Now let's go to some computational experience. Yes.
Even though you know this conservative thing about you're not too close to the arc to the path, the previous one.
Yes, this one, right?
So what is the traveling at different speeds? Even if you arrive at the right speed, if one coming in the diagonal is faster, won't that still create trouble later?
Well, okay, so like this is like we are basically considering the situation separately, in the sense that here we just impose the constraint on this node. So meaning that we allow, so we ensure that this flight will not go in this in the trajectory of the other flight, like before it can reach. So this is clear, but then later on, so the next step can be any of the other cases. So we treat them separately, but they will be all present in our constraints. So after this, you can have a situation in which you have yeah, like diverting or splitting, etc. So they will be all covered by these three cases. Okay, some computational results. So we consider three topologies. So these are kind of schematic topologies, but you can see that the axes here are the vertiports. And so 1, 2, 3, these were provided by, so of course the service doesn't exist yet. So we are realistic instances, let's say. Realistic because we had our colleagues from Uber that provided these topologies that for them are realistic. And then we generated some instances, as I said, we consider 3 scenarios, and for each of the topology we consider, and each of the scenarios we consider 20 instances, generating them by batches of flights that regularly were planned to leave from each of the vertiports and arrive to other ones. And then for the scenario 3, the intruder one, we had 180 instances because for each topology and each 20 instances, we had 3 different values of R, which is how much time we have to react before the intruder enters the corridor actually. And this is, of course, decreasing complexity. So the more time we have to react, the more likely it will be that we can find a feasible solution. or a rescheduling. Okay, so scenario 1. So there are a lot of information, but we'll focus on only a few of them. So we have the 3 topologies and the average. So for each of the topology, we have the CPU time. I want to focus on the maximum CPU time. It's always less than 2 seconds. So we could be like pretty fast in solving the problem or proving that there was no feasible solution. In this case, there was only one instance over the whole set of instances that was infeasible, but proved within 2 seconds in any case. And then we had, I think the more interesting thing is like the deviation, of course, this the mean deviation per flight and per node, which can be, I mean, it's limited. So the overall, if of course it's large, but then delay at destination, we had on average number of trips that were delayed is from 5% to 28%, more or less. And this is the maximum delay per flight. Then we have some information about the speed changes, but I want to focus on this part. This part is what we will gain if we had like about the, like what was that? So the deviation, like if we have a 10%, we allow 10% of changes in the speed instead of only 5%. The scenario 2 is pretty similar. Here we have no infeasibility. We have always less than 2 seconds CPU time to converge to the solution. And yeah, so the maximum delay at destination is also limited here. I think the most interesting part is also the scenario 3, in which unfortunately we have several instances for which the infeasibility is proven. It's proven pretty fast here, and when we allow more changes, so 10% of speed changes, we have some instances that become feasible, 10 in total over the wall here. And this is of course an issue, but still we have so we are working on trying to improve this. And now I want to just to consider some comparison with what was the state of the art before this paper. The state of the art was some local approach in which, so it was an iterative algorithm in which at each iteration a conflict between 2 aircraft was identified and solved. And so it's a kind of myopic view, because you do not try to find the best schedule, but you try to fix one conflict at a time. And so here on the left, I don't know if you can see it, but for each of the topology, we have so this is the deviation, the total deviation of the optimal solution. You can see that, so the light gray one is the global approach and the other is the local. You can see that we have like way better results at the cost of larger CPU time, which is represented here, but still we were solving everything in less than 2 seconds, so it's acceptable, let's say. Scenario 2 is even more clear, the difference between between the 2 approaches, both on the deviation and the CPU time. But again, it took us 2 seconds to find everything, so it was good. Scenario 3, I didn't have a plot because actually, like in the local approach, they could only solve 3 over 180 instances, which we actually had way better results because number of infeasible, like 128 for us. Okay, now like our thought based on the fact that we have still several infeasible solutions here is, okay, can we try to solve the strategic problem in order to make it more robust to disruptions? That is one of the things that we thought about. And so the idea is, so we modeled the problem as a 2-stage robust planning. in which we have like the outer problem is finding the nominal schedule, so like the schedule that we have in advance, that we want to compute in advance. So P is represented just a feasible solution set of the scheduling problem that we have seen before. And then we want to find the gamma values, which represent our uncertainty set, which is the worst case uncertainty that we can find. And then minimize over the re-optimized schedule. So we have here T hat, that is the nominal schedule. T in blue here is the re-optimized schedule. And then we have some constraints about the uncertainty set. We have a budget value, gamma, capital gamma. This is the uncertainty budget. And then we can spread it, so these are variables, along all the flights. And this will influence only the departure time of the flights. And so we have actually that the new schedule has to be greater or equal than the planned schedule plus the uncertainty, so the delay that we impose to the flight. Is this clear? Okay. So now, what did we do? So we applied a kind of adversarial Bender's decomposition to this. And oops. Okay, and then the outer problem is a mixed integer linear problem, but I want to focus on the inner problem, which is a max-min problem of like with this this side. So what we tried so far were these approaches. First of all, to solve the sub-problem here, recall that if we didn't have any binary variables, that we could reformulate it, dualize it, and then make it just like a unique problem, etc. But like we have actually binary variables, so we cannot do it. So we decided to explore a local search, like algorithm based on the fact that we can prove that actually there is an optimal solution of finding the worst case scenario of the uncertainty that has a strict strict inequality, so we have an equation valid here. So what we do is to explore the neighborhood given by the fact that the sum of the gammas has to be equal to capital gamma, so the budget constraint, we use all the budget, and then we explore a kind of neighborhood of the current solution. Like the current solution is the gamma here, and then gamma prime is the alternative solution of this that we want to find. Once we fix the values of gamma, of little gamma, then the other problem we know how to solve it, because it's just the tactical problem that we solved so far. Then the alternative is, okay, so let's see what happens with the dualization. So the binary variables allowed us to model the disjunctions that said, well, you can change the order in which the flights are passing through a node. Now, let's see what happens if we keep the same order. And so at this point, we do not need disjunctions anymore. And so we can dualize it. And we have either a quadratic program, or we had actually this situation in which we could compute a recursive formula for computing the delay of each of the flights. I think I don't have time to explicit, so let's say, yes, 10 minutes, to explicit this. So okay, because I want to show you some results, maybe. I will go to this, sorry. Well, if you want to see the model of the tactical deconfliction, it's here in 2 pages. And then I didn't speak about the Fermis, but maybe, yes, so here we have some computation about the strategic planning, comparing the local search, the quadratic version, and the other version is a mixed integer linear program. Actually, I don't know. I thought I had a slide on the model that is resulting from this, but actually exploiting this recursive formula we can write the subproblem as a mixed integer linear program that we solve. It's an exact one. And then, yeah, with some results. Yeah, so here we have for each of the topologies that we've shown before, and for different values of uncertainty sets, we have 10 or 20 uncertainty set. We have the average, the time, and the number of iterations. So basically, you can see that the time here is like larger for the local search, maybe because the search is not done. Like it's a larger problem, of course, because we are also having like allowing the changes of the order of the flights. So here we have similar results for the quadratization and for the MIP, for the subproblems. But then as we change the topology, they also change. So it looks like finally the quadratization from what concerns the time is the best. Of course, we are limiting ourselves to a case in which we do not change the order. So we think that it's less likely that we will find more solutions because we are restricting our problem. And so it's also interesting to solve with the local search for this reason. And then I would like to speak briefly about what we are doing now, which is trying to have other alternatives to make more instances feasible. And in particular, one of the things that I told you at the beginning is that we do not allow changes of the path. But now, what if we do not have any choice? So we have an infeasible problem if we allow only speed changes and departure changes. And so we allow only in that case some path changes. So for example, we can go from this red here to the blue using this path, but we could have also picked this one. And so we are currently working with Tom and Filippo Maggi, a master student who is visiting. We are trying to solve the tactical problem, allowing also the path changes. Of course, the model is very complicated, and unless the instance is small, we cannot solve it exactly. But we are exploring an alternating projection algorithm to converge, and it converges to a solution pretty fast. I do not have exact the tables now, but I think the tests are running. So, and then the second option is, so when we decided how to simplify the separation constraint, I told you several times that I made it as simple as possible. And in order to do so, it was more conservative than it was needed. And so the other possibility could be to try to think about less conservative constraints, which are still can be tackled by the solvers, or having a specialized algorithm on the topic. And then, of course, another point is that the corridors have to be designed. So they are not given, so they are not built. So one can think about designing corridors so that allows redundancy and extra corridors to allow the change of the path in case of problems. And then, so I would like to end with a small advertisement of MIP Europe. So it's the first time we organize a MIP in Europe, and it will be in this summer. So if you want more information, I'm happy to answer, and I'm happy to answer also to the further questions.